All right, this is our third class on Chapter 22, Electric Potential and Electric Potential Difference. And I want to just kind of remind you what we were talking about at the end of our last online class. We were looking at equipotential surfaces. And again, these two diagrams are similar to what we did in the lab where you guys plotted equipotentials and electric field lines. So again, it's important to understand the relationship between the two. In the lab, you guys determined that the electric field lines and the equipotentials are always perpendicular to each other, and that is correct. And if we look at the electric field, notice that the electric field again always goes from a higher potential, so like 20 volts, to a lower potential, 0 volts. Okay, so it's always in the direction of decreasing electric potential. Again, if this plate is at 12 volts, and this electrode is at 0 volts, notice the electric field lines go from higher voltage to lower voltage. And that's the significance of the negative sign in the formula. Also, the significance of the dot product, it shows us that the maximum change in potential is in the direction of the electric field. And again, we talked about that if you think of this as a topographical map, basically the electric field is the steepest way down through the electric potential. All right, I want to bring up a simulation. And so I'd encourage you to try this on your own. Again, just go to phet.colorado.edu and look for that charges and field simulation, or try to copy and activate that link. Let's take a look at this simulation showing electric field lines and equipotentials. So first of all, by default, electric field is checked. And you'll notice that if I take a positive charge and a negative charge and set them up here, we get the electric field lines that we would expect, right? So this is the electric field of a dipole. We can see that the field lines are leaving the positive charge and are going towards the negative charge. One of the things that I can do with this simulation, though, is I can also look at what the voltage is in the same area of space. So here's the key idea. If I've got charges, then I have both an electric field at every point in space and a voltage or electric potential at every point in space. So let me click voltage, which again is electric potential. Now remember, potential can be positive or negative. The way the simulation is showing a negative potential is blue and a positive potential is red. What's probably more useful, though, is to take this little probe that shows me what the electric potential is at a point in space. And so you'll notice as I get closer to the negative charge, it's getting more negative. If I get closer to the positive charge, it's becoming more positive. I'm going to try to find the point where it's just about 0, which is right about there, and I'm going to click the little pencil. Notice I've just drawn the equipotential for that voltage. Let me go over and find the equipotential at negative 4 volts. So I'm going to find roughly negative 4. Whoops. And then I'm going to click the pencil again. So that's the equipotential at negative 4 volts. Let me go over here and find the equivalent for positive. Okay. You'll notice we could have done that whole lab effectively with this simulation. So there again was the negative 4 volt equipotential, 0 volts, and positive 4 volts. Notice that at any point where you see a field line crossing the equipotential, notice it always crosses perpendicular, like you saw in the lab, and also that the electric field is always in the direction of maximum decreasing electric potential. So it's towards the negative charge because that's where the potential is negative. All right, now that we've looked at the simulation, I want to show you that not only can we find the electric potential difference from the electric field, but we can also go the other way. We can find the electric field if we know the electric potential. Now, this is actually a topic that normally you don't see until Calc 3, um, but, um, but as long as you're in Calc 2, which is where you have to be in the course, I can show you what you need to know to understand this. So you'll notice that I keep saying that the electric field is in the direction of maximum decrease in electric potential. Well, if you were thinking about that at all, you might have realized that that sounds like a derivative, right? Now, the only thing is, it's a little bit more complicated than derivatives you've seen before. The process that we use to find the electric field from the voltage is more complicated because remember that V, electric potential, is a scalar. And E, electric field, is a vector. So how do we get a vector from a scalar by taking a derivative? Well, it turns out for those of you who are going to take Calc 3 if you're in engineering or if you're already taking it, you will learn that it's called taking the gradient. So taking the gradient. And I'll just tell you what it actually looks like in Calc 3. Again, I won't require you to know this particular thing, but the way that we write it in Calc 3 is that E is equal to minus del, so that's called the del operator, times V. Don't worry about that if you've never seen it before, but just for you Calc 3 folks, I want to throw that in there. But this is what I want you to understand, which is what is that del? What does that mean? Well, it's just taking derivatives. You'll notice when you look at this formula, though, these look funny. In other words, instead of a usual d for derivative, we have a lowercase delta. And that's because these are called partial derivatives. And partial derivatives are a little bit different than regular derivatives. So let's talk about why we need a partial derivative. What's different? Well, here what we're saying is that there is a voltage or electric potential at every point in space. So think about it. Electric potential or voltage is a multivariable function. In other words, there is a voltage for every point x, y, and z in space. So with a multivariable function, then when we take a derivative, we have to specify which variable we're taking the derivative with respect to. And so that's why we have dx, dy, and dz. The reason the notation is different is because when you're taking the derivative with respect to x, you treat y and z like they're constants. When you take the derivative with respect to y, x and z are constants, etc. Okay, so let's see how this works. So here we have a question. What is the electric field in a region where the electric potential varies as V is equal to 2yx plus x cubed z squared? So in other words, remember that the electric potential is defined at every point in space. So in other words, if I wanted to know the potential at a particular point in space, if it's given by this formula, I just put in the x and y and z values, and I would just get a number for the electric potential. What we now want to do is find what would the electric field be at a point in space x, y, z. Okay. Now again, it's a vector, not a scalar like potential. So we want to implement this formula, and let's look at how we take those partial derivatives. Well, dv dx, I want to just take the derivative like you know how to do with respect to x and just treat y and z like any other constant. So the derivative of x we know is 1. The y is just a constant, so it just hangs out like the 2, and we get 2y for the first term. The second term, we have z squared, which is just going to be a constant, and then the derivative of x cubed. So that would be 3x squared, and then we'll just keep the z squared right there at the end. Okay, so that's the partial derivative with respect to x. With respect to y, we see the first term has just a y, so the derivative of y is 1. So we get 2x. Again, x is now just a constant. Notice the second term doesn't have any y in it. It's just a constant. Well, the derivative of a constant is 0, so that's all we've got for dv dy. dv dz, notice that the first term does not have a z in it, so it's just a constant. Derivative of a constant is 0. And then the second term, derivative of z squared would be 2z, so 2x cubed z. And those would be our 3 derivatives. Now, once we've got the derivatives, we can now assemble our answer for E. Notice, first of all, this minus sign. It's really easy to forget that. So I'm going to write negative parentheses 2y plus 3x squared z squared times our unit vector I. Remember, that's just a vector with a length of 1 that points in the x direction. dv dy, I have minus, so I'm distributing that minus sign, minus 2xj, and then minus 2x cubed zk. So that would be my answer. And if I now wanted to know the electric field at a particular point in space, I could plug in x, y, and z, and this would give me the vector for the electric field at that point in space, x, y, z. All right, why don't you try this one on your own? So I'd suggest you pause the video and try it on your own just to make sure that you're understanding this. All right, so let me just give you the answer. dv dx. So when we take the derivative with respect to x, that's a constant. Here we would just get 2y cubed times x. For dv dy, we would get z plus 3y squared x squared. And then dv dz, only the first term has a z in it, so the derivative of z is 1, and so we would just end up with y. And now to put our answer together, the electric field at any point would be equal to negative 2y cubed x times I minus parentheses z plus 3y squared x squared j minus y times k. So hopefully that's what you got for your answer. Continuing with the problem, we could now ask, well, what is the potential and what is the electric field at this particular point in space? So now we're just going to plug into the formula. For V, we get yz plus y cubed x squared. And so I just plug in the values. In other words, y is 3, z is negative 1. Then I've got 3 cubed for y, and I've got negative 2 squared for x. And again, if you want to stop and try this one on your own before you look at the answer, that's always a good idea. When I calculated the math, I got just 105 volts. So remember, electric potential as units of volts. And notice it's a scalar. It's just a number. It could be positive or negative, but it's just a number. Now let's look at the electric field. So I'm going to plug into this formula. I've got negative 2 times y cubed, so that's 3 cubed, times x, which is negative 2, times I, minus parentheses, I've got z, so negative 1 plus 3 times 3 squared, negative 2 squared, j, minus, and y is 3, so 3k. Now, I'll tell you what is a common mistake students make on the exam. They often just forget about the i's, j's, and k's or drop them. Don't do that. Remember, E is a vector. That means that if we're leaving it in vector form, it's either got to be a magnitude and a direction or the components with i's, j's, and k's. So what I ended up with for my answer was 108i minus 107j minus 3k. So that's my answer. Or if I wanted to just give the components. So I think in one of the homework questions in Mastering Physics, it just asks you to put in the components. So the components would be 108 for the x component, negative 107 for the j component, or y component, I should say, and negative 3 for the z component, okay? But generally, it's nice to leave it in unit vector notation. So again, the key thing to understand is the electric field is a vector, field. I want to go back just a second and just, again, show you or talk about the significance of this formula. Remember how I keep telling you that the electric field is always in the direction of maximum decreasing electric potential? Well, this is how you do that mathematically, okay? So if you've got a scalar field like electric potential and you want to find what is the direction of maximum decrease, then that's how you do it, okay? And again, that's called taking the gradient in Calc 3. Let's look at the following question. It says, if the electric field around a conductor is high enough, greater than 3 times 10 to the 6th volts per meter, then the oxygen and nitrogen molecules in the air will be ionized and the air will become conducting. So, by the way, we know that air is, I think it's about 78% nitrogen, and it's like 21% oxygen, and then everything else is just that small percentage that's left over. So when we think about air molecules normally, well, it's mostly nitrogen molecules and oxygen molecules floating around. And obviously molecules are normally neutral, so normally air is not conducting. But if the electric field gets strong enough, remember that if you've got an atom, and let's just talk about a very simple atom like hydrogen. So we've got our negative charge surrounding our positive charge. Well, if we put that into an electric field that's pointing in this direction, you'll notice that the positive charge wants to go in the direction of the field, since F equals QE, as we've talked a lot about. But notice that the electron, because it's a negative particle, wants to go in the opposite direction. And therefore, what we find is that if you put an atom or a molecule in a strong electric field, if it's strong enough, you'll start pulling outer electrons out of the atom or molecule. And that's how air can become conducting. All right, so now here's the question. And of course, I forgot that was going to show up right there. So hopefully you remember what I wrote. Which of these conductors could be raised to a higher voltage, A or B? So the question is, I'm going to start getting breakdown or lightning. In other words, sparks are going to start going off once the electric field at the surface of the conductor becomes high enough to start ionizing the air. And so the question is, which conductor, a big conductor or a small conductor, could be raised to a higher voltage before I would start getting sparks, before the electric field would get that high? So think about that for a second, and then we'll talk about the answer. Well, it turns out that the larger one could be brought to a higher potential before you started getting sparks. And we can see why this is. We know how to find the electric field anywhere at the surface or outside the surface for our conductor. It's just the same as the point charge, kq over r squared. Remember, we also now know how to find the electric potential at a distance r from the surface out of a conductor. So you'll notice these formulas look very, very similar, except that V only has the r in the bottom instead of the r squared. Therefore, you'll notice that V is equal to r times E. And specifically, if we're looking right at the surface, V is equal to r naught, where r naught is the radius, times E. So that means that since E is the thing that's determined, in other words, when E is equal to 3 times 10 to the 6th volts per meter, that's when I start breaking down the air. But if E is equal to, well, actually, let me just leave it there. So in other words, that's the same no matter what. Notice then the bigger that the radius is, the higher the voltage at the surface can be before we get that breakdown. Now, there's kind of an interesting example of this, and that is the Museum of Science Van de Graaff generator. So many of you have seen the electricity show at the Museum of Science. If you haven't, again, I really encourage you to go to it. It's a fun thing to go see. Well, the Van de Graaff at the Museum of Science was originally at MIT. And the reason that it was was not built as a demonstration device. It was built for experiments. And the idea was they wanted to be able to get those domes up to a very high voltage. Well, what we just learned is that if we want the highest voltage at the surface, or actually the voltage anywhere outside the surface, then we need R to be as big as possible. And so that means that the Museum of Science Van de Graaff can be brought to very high voltage. By the way, you'll notice how big a person is. Our little Van de Graaff generator is about half a person tall, so that's kind of, I've put it in there for scale. Obviously, the Museum of Science Van de Graaff can go to a much higher voltage than our Van de Graaff generator. Let's talk just a little bit about how a Van de Graaff generator works. We talked a little bit about this before, but again, remember that since charge always wants to go to the outside of a conductor in electrostatic equilibrium, basically what we do is we just keep putting charge on the inside of the conductor by it coming up this little conveyor belt, and then that charge immediately goes to the outside. And so basically we can just keep putting more and more charge onto the Van de Graaff until the electric field gets to the point where it starts breaking down the air at the surface. So here's a question. What's the maximum potential our Van de Graaff generator can reach? Assume the spherical conductor has a radius of 0.1 meters, and how much charge can it store? All right, so we know a couple things. We've said that at the surface, V is related to the electric field in this way, and we know in general that the electric potential created by a sphere of charge is kq over r. So to figure out what is the maximum electric potential that our Van de Graaff can get to, we just need to put in the radius and that breakdown electric field voltage. Again, if the electric field gets to be 3 times 10 to the 5th newtons per coulomb or volts per meter, that's when the air breaks down. So we get 0.1, sorry, got that value wrong, correct that, 3 times 10 to the 6th. I was jumping ahead to the answer. So we've got 0.1 times 3 times 10 to the 6th volts per meter times 0.1 meters, you'll notice gets us to volts, and that would be 3 times 10 to the 5th volts, or 300,000 volts. So our little Van de Graaff generator can get up to 300,000 volts. And unfortunately, I won't get to demonstrate that to you. It doesn't look like, but that's legitimately about what it can get to. Now, the second part of the question is, how much charge does it store? Well, now that we know V, I can use this formula to find Q. Q is going to be equal to V times R divided by K. And I'm going to use R naught there because I'm specifically at the surface. And if you go ahead and calculate that, and I'll let you do that on your own, you should get 3.3 microcoulombs. So one of the questions that people often ask in class is that voltage dangerous? Because it certainly sounds like a very high voltage. And in general, we think of high voltages as being dangerous. But it turns out, if we had been in class, I would have let you, if you had wanted to, take your hand and put it near the Van de Graaff. Here's your hand. And let it spark to your hand. And I've never killed a student yet. So that's a good record, right? And so why isn't that deadly? Well, the reason is that it's not very much charge. So that charge hits you pretty much all at once, but it's a small enough amount that it doesn't cause any damage. It hurts, by the way, but doesn't do any permanent damage. Let's compare what would happen if we did the same thing at the Museum of Science. Just to make it simpler, I'm just pretending the Museum of Science is just one dome, like our Van de Graaff. The size of the Museum of Science Van de Graaff, it has a radius of 2.25 meters. So to figure out the electric potential at the surface, again, it would just be E times R naught. So that's 3 times 10 to the 6th volts per meter times 2.25. And what we end up with is 6.75 times 10 to the 6th volts. Okay, so, that sounds a little bigger. Instead of 300,000 volts, we've got 6.75 million volts. So, yeah, that's a little bigger. But what I want you to notice is that when we now solve for the charge on our Van de Graaff, we have V R naught over K again. What you'll get when you calculate that is 1,700 microcoulombs. And so again, I encourage you to check my math and make sure that you get that as well. What I want you to notice is that is substantially bigger than what we got for our Van de Graaff. For our Van de Graaff, it was 3.3. And you'll notice that the reason that is, when we calculate V, it's multiplied by R, but when we calculate Q, it gets multiplied by R again. So it really goes as the square of the radius. That amount of charge hitting you all at once is not a good thing. That would kill you. So the moral of the story is, don't run inside the cage at the Museum of Science.